we're gonna finish up neural networks today, and today is really like the last stuff I definitely wanted to get through. We have 2 classes next week where I'll give you options on what you guys want to do, and so there'll be a question where I'll say, which of these do you want to learn about next week? And there's some options, and I'll go through them very quickly, in like 5 or 10 minutes to give you a flavor of what they're like, and then depending on what people are interested in, we can learn something fun and cool next week. Other reminders, the data sets for the final project are up on CampusWire, so go vote for the ones you like. Probably you guys already did that. And your project 2, you should have your draft back now with comments from the peer reviews and the TAs, and that's due on Tuesday next week for the final submission. Any questions or comments about anything? Yeah.
Yeah. Which review is of TA?
Yeah. Sorry.
Which review is of TA? That is no indication.
Okay. Well, so the TA's name is. You can't see the name. Okay, that's interesting.
Last time we were able to see some settings like symbol, gear, but this time all are looking.
They look the same. Okay. Yeah, and I guess it's anonymous. It doesn't tell you their name, right?
Yeah.
Okay. Yes. That's interesting. Okay, I'll look into it and see if there's a way I can tell you which. I probably the TAs is like a little bit longer on average, but yeah, I can.
Actually, all look same. Actually, students.
Okay. Well, so I mean, if they're sort of indistinguishable, that probably means people did a good job. Okay, I will look into it and see if I can look for you. If you really need to know, send me an email and I can look on a case by case basis. But it should be helpful no matter what. Right? Like,
yeah.
Especially for things like, is it human readable, right? Is the executive summary a good summary of what you did? You could ask somebody on the street, right? Stop, excuse me, sir. Do you understand what I'm doing? It's like, it's a valid thing. So yeah, but if you really need to know, just email me and I can do it. I didn't realize that would happen. That's funny. Okay. Great question. Anybody else? Questions or comments? Okay, so we're going to pick up with what we did last time. And last time, we spent 2 classes on this one Google Colab. And it was the MNIST example, so we did the MNIST data set. And we really went from starting with nothing to getting like 98% accuracy on MNIST, right? We started with loading the data. We wrote down all the functions by hand. All of the functions we wrote down with our own hands in terms of things like sum and dot products and things like that. Okay, I guess it's a lie. We didn't do the loading the data set. The loading the data set we just copied from somewhere. But other than that, we did all this thing of like splitting it into training test set, and then we wrote the functions that do it. So generating the random parameters, things like that. And we did linear regression, then we did logistic regression, and we talked about how to upgrade that. And then we eventually did an actual neural network that got very good performance. And the performance, I think it got at the end. But the very last thing we were looking at is it had something like 98% accuracy. Where does it say its accuracy? And its accuracy was 98% accuracy on the training set, and its test accuracy was 97.25%. So very good accuracy. And we were looking at like the examples that got wrong are all mostly messed up examples, right? Like kind of unusual ones. It gets all the ones where it actually looks like a 5, right? If the digits are a little messed up, then it can make a mistake. And the question is, one thing we learned about in the course is this idea of overfitting and underfitting. This model you might not think about as being too overfit right now, because you might say, okay, well, the training accuracy and the test accuracy are both in the high 90s, right? 98.4 and 97.25. But you really should think about it when you get to numbers that are close to 100 like this. You really should think about the error rate, right? Sort of making the model twice as good would be going from 98 to 99%, because the error rate goes down from 2% to 1%. So the error rate is 1.6% on the training set, and the error rate on the test set is 2.75%. And 2.75 is quite a bit more than 1.6. So even though these numbers, if you look at them out of 100, look pretty close. If you look at the error rates, it's actually overfit by a little bit. It's sort of over-memorizing the training set. And one way you could improve it is to try to make it overfit less. Try to bring those 2 accuracies together, right? So the training accuracy will go down a bit. The test accuracy should go up a bit. that's what we learned about on our first project, was this idea of overfitting versus underfitting. And one way you can do this is you can add in regularization. We talked about that. Ridge regularization or lasso regularization. And both of those, in our Legoland world of building neural networks, fit in quite easily. And that is the question in Mathematize right now. How would you add in ridge regression or L2 regularization? All you have to do is blank the blank. All you have to do is blank to the blank. And I want you to fill in what that is. So, and again, they're words. You can fill in any words you want. And I suppose there's many right answers. But how would you describe to somebody what you have to do to make it work? And I'll give you, say, 30 seconds or a minute. I guess 5 people have already put in there. So let's do 30 seconds. Put in what you think it could be. How would you do it? And it's I'm telling you, there's a very simple way to do it. Given everything we've done in the last 2 classes, it's like a one-liner to make it do that. It's not a whole complicated thing. It's a very quick, easy way to do it. Okay, we're up to 7 answers. The last few people, get your answers in. If you haven't yet, I'm going to hit the button in just a second here. So put in and hit submit. Okay, let's see. What did people say? People said you should blank to the blank, where the blanks are. First blank, add L2 regularization. Yes, right, so that's what we're doing. Ridge regression is adding something. I think this adding is doing a lot of the heavy lifting here. This is good. We're going to add something to something else. What else did people say? Add, okay, great, add. Okay, it won't let me scroll down. Okay. So somebody said add penalty, also great. So regularization term is the thing we're doing. What's the verb? Is something to do with adding. So we're going to add something to the loss function. Very good. So if you said loss function, that's exactly right. These other things are related to what we're doing, and it's the loss function. That is the thing we're changing. And if you go to how we built everything last time, remember, we had this whole system of what the neural network is doing. How does it go from inputs to outputs? But then equally important was how do we judge how well it's doing? That is the loss function, right? And I think that is written somewhere over here. We spent some time working on this cross-entropy loss, right? The loss function is the cross-entropy loss. And that had a funny formula, right? It's the sum of pi times the log of p hat I. We talked all about that last class. That's the ordinary cross-entropy loss. And if you want to make it regularization, you want to add on with L2 regularization, also known as ridge regression. All you got to do is add on a term that says, but also, please make it minimize the sum of the squares of the weights. So the sum of the squares of weights. And there's lots of ways you can write that. You could do the sum. You could say wi minus. No minus, just make them small. Minus wi squared. And you sum over all the weights. So this part, the blue part, the cross-entropy loss, really depends on the prediction. You take your final prediction, you're judging how good the prediction is. And this part tells you, okay, but how much work did you have to do? How big did you have to make the weights? And by doing the sum of them, the neural network will try to make both of those small, right? Because when we do gradient descent, we're shrinking the loss function. And if the loss function includes this plus regularization term, it makes that small as well. There's one other important thing to tune, which is to put in some parameter alpha so that you can balance these two things against each other, right? Because if you make this number too big, then it will not try to be very accurate. It will just make the weights all 0, and that won't do well. And if you make that number too small, then it's like we're not doing anything. So you got to find a balance. And again, we talked about that. You can make those plots where you vary alpha and see how the predictions work. And in our thing, it's very simple because, why is it very simple? Because all you have to do is go to where the loss function is defined. So before we were doing the CE loss for the MLP, and here's the CE loss for the MLP. I can just copy paste this and make a new one. Let's make a new one called the CE loss for the MLP with regularization. And let's be specific and say L2 reg. And all you got to do is So I'm inputting the parameters, the images, and their targets, like what their true labels are. And we have this whole system for the cross-entropy loss. And it works because one of these, the predictions are actually the log probabilities. So the preds are the log probabilities. This is the log of p hat times p. And so this first term is doing exactly the term in blue, the cross-entropy loss, pi log of p hat I. And now we're going to add on just the other term. We can just add on the other term. And so to do that, I will just add on plus alpha. We're going to make alpha the regularization. Alpha is regularization strength. And I don't know, we'll make it 0.1 or something. Okay, you can add it on. And then we're just going to input. We have the params there, something about the sum of the squares of the parameters. To do the sum of the squares of the parameters, you could do jnp.mean, and then you could do params squared. That'll take all the parameters and square them up, and then add them up. This will be the average. That way, if we add more parameters later on, if we go from 784 to 1,000, then it'll still be a meaningful number. We won't have to change alpha. Otherwise, alpha will have to scale with the number of parameters, which is annoying. But very simple. All you literally have to do is add this term on, and everything will work. It will just automatically do the regularization for you, which is very nice. Okay. Any questions or comments about that? So this is, we're getting to the point in the course where we have enough things that we've studied already, we just combine them and get new things, right? So we learned about regularization, we learned about neural networks. Now we're just combining them, and it turns out it's very easy. If you understand how both of those work, you can build up to new things right away. Questions or comments? Okay. Yeah.
Is the alpha that we are selecting here like the same way that we are doing in the simple regularization, or like do we have to consider any other factor?
Well, yeah, so I think the alpha plays the exact same role that alpha did before. When we did it, I think we did ridge regression for linear regression. It's exactly the same concept. So however you were thinking about alpha in your brain before, think about this alpha the same way. And I just hard-coded in alpha equals 0.1, but in reality, the way you test is you just try a bunch of different alphas and you see which one has the best test error. And if you make it too big, you're going to get really bad error, or you're going to have that U-shaped curve again, where if it's too small, you're overfitting and you're not doing as well as you could. If it's too big, then you're underfitting and like it's not doing well, and there's a Goldilocks spot. Is the Goldilocks spot at 0.1? The only way to tell is to try a bunch of experiments. Yeah. So people call this a hyperparameter, and finding the best alpha they call hyperparameter tuning. Of course, in our neural network, we also have a bunch of other hyperparameters, things like how big should the layers be, how many layers should there be. All of these are kind of made up, and the only way you can test is to really go out and test it on your data set and see what has the best test error, right? And yeah, I mean, there's like good rules of thumb, but at the end of the day, you gotta just go test it. So I put it in 0.1, and if I really wanted to run it, I would test it. Great question. Anyone else? Okay, so in the interest of time, I'm not going to run it. If you run it, it'll look very similar. It'll take you a long time to run everything, and this will go up. Instead of being train of 98.43 and a test of 97.25, you'll get something like both of them are 98. Okay, so you've gotten a little bit better on the test set and a little bit worse on the training set by adding in regularization. And this is summarized quite nicely in that video that I assigned you. So this is the textbook we've been doing, the statistical learning textbook video on neural networks, and at the end of their video on neural networks, they report the training errors for, the test errors for different methods. And the top of their table is neural networks with ridge regularization, and they say 2.3% error. So that's right around 98%. Right, it's very slightly better than what we have right now. Right now we have 97.25, they have 97.7, so like a little tiny improvement. And they say you can get even better if you do something called dropout regularization. And dropout regularization, again, same kind of idea as ordinary regularization, but dropout is something you can do in a neural network that you cannot do in linear regression. And I really think of it very similar to how I think about the regularization of those robots when people kick the robot to try to make the robot robust to changes. Dropout basically says, what if our neural network had problems where neurons would randomly turn off? So in dropout regularization, you take the graph of our neural network, which looks like this, right? And maybe it has many layers. And every time you run it, we kick the robot. What does kicking the robot mean? It means you take your pen and you randomly turn off some of the things. So you just take your pen and you just say like, this one, cross it out. This one, cross it out. This one, cross it out. Just like start deleting things at random. So it's like the version of kicking the robot, but on the neural network. Of course, that makes the neural network worse. The same way adding a penalty makes it worse. But when you do this, the neural network has to be very robust to changes, right? So when it tries to achieve good performance on this thing where it's randomly getting kicked all the time and neurons are getting turned off, that will lower its ability to memorize examples. Because for example, before, it could say like, this neuron will just memorize the first example. This neuron will just memorize the second example and so on. But now you're turning off neurons at randomly all the time, so it will do really badly on the training set even if it has this strategy. So what it actually has to do, the only way it can find a good solution is to not memorize things and really like learn the patterns in a robust way that's spread across all the neurons so that when you randomly delete things, it still does well. So that's dropout in a nutshell, and that improves the performance by a little bit. Dropout. There's another video you can watch on this, and this is one of the topics we could do. We could do more neural network stuff and learn in more detail what dropout is, but very roughly, that's what it is. The other two are things we've done before. So logistic regression, we even did that in our notebook. We got like 90% accuracy. And if you do linear discriminant analysis, that's something else we talked about, very simple method, then you get like 80% accuracy, 88% accuracy. Later in the video, if you watch it, you'll see that they mention you can get to as low as 0.5% error. And to get 0.5% error, you can use more advanced neural networks. So there's something called a convolutional neural network that is really well designed for images and works well on images. And if you use that one, you can get the error rate even lower. And that will be one of the options that we can do next week, is to learn more about these convolutional networks and more advanced like image processing techniques and how they work. Okay, yeah, and again, some of these are in the videos as well. So if you're interested, you can also just go watch and read from the textbook as well. Okay, any questions about these regularization or sort of this MNIST stuff that we've done so far? Okay, so you can think about everything we've done so far. We've had X's and Y's. And the first half of the course, we did it the sort of traditional methods, linear regression, logistic regression. And in the last two classes, we've upgraded linear regression and logistic regression to neural networks. And that is the classical X and Y setup. That's the supervised learning setup. You have X's and Y's. You got to learn how the X's make a function that maps X's to Y's. But of course, neural networks can do all sorts of other things. They're just general functions. You can use them for anything. And here is another thing you can use them for. Here's another thing you can use them for. So here is a really wonky network. So it's got layer sizes 784 to 784. So already this is quite weird. Before we had the final network was the output, and that was size 10. Okay, so that's what we did before. Now the final network it looks like this. I mean, it's some kind of like big, small, big network. So 784. 784, and then we go down to 2, and then we go up, back to 784. 784. All right? So it's a very weird network where the output size and the input size are the same thing, 784. Okay, what are we doing? That's one thing. The layers are fully connected matrix multiplies with no nonlinearities. So again, this is a simplified version of a network with no nonlinearities. Once we understand what this one is doing, we'll upgrade it by adding in nonlinearities, and that'll be like giving it superpowers and letting it do all sorts of cool stuff. But first, let's see what happens when it's linear. Okay, so it's linear. There's basically two matrices. There's this matrix, which is going to be 784 by 2, and then there's this other matrix, which is going to be 2 by 784. Okay, and so this is going to be W0, and this is W1. It's got two matrices like this that are long, skinny matrices. And they're acting linearly. So the output is y is W1 times W0 of x. This is the output, and this is the input. All right. And I'm going to do a really weird loss function, not cross-entropy loss, not the mean squared error loss. although it does look a little bit like the mean squared error loss. It's that loss function. So I'm taking the input xi, and I subtract it from f, that's what I called y over there, and I do the norm squared. So this function is what I call f of x. Theta is this, where theta is the set of parameters. That's w0 and w1 together. If you have w0 and w1 together, those are the parameters. Okay, so that's the loss function. It's kind of like the mean squared error, but of course there is no y, so it's not actually the mean squared error. And I want you to think about what this network is doing. So it's sort of unsupervised. I never look at the y values. What would this do on the MNIST data set? You apply it to the MNIST data set where the x's are images, and you tell the neural network, as always, you tell it, please minimize the loss function. Find parameters that make the loss function as small as possible. Okay, I'll let you think for a minute. This is actually related to something we saw earlier in the course. So if you think hard and understood what we did earlier, you will figure out what this network is doing, and then when we go to upgrade it, you'll see we're doing an upgraded version of that. Okay, let me give you 2 minutes to think. Feel free to chat with your neighbors about what this thing could possibly be doing and what's the point of all this. Okay, who needs more time? Okay, a couple people. Let me give you another minute. No problem. Yeah, think back to the things we did in the course. Which one could this be? Okay, so before I reveal the answers, does anybody have any questions or anything about, maybe someone came up with something they didn't quite understand while they were thinking about what's going on here? Is the setup clear? It's a bit unusual, right? Like there's no y's. I think that's the biggest weird thing. There's no y's. What could it possibly be? What's the point of doing things with no y's? But questions? Okay, let's reveal, and I'm sure that'll generate some discussion. What could this be? Oh, not working. Okay, let's try closing this. Going back. All right. So this thing is called an autoencoder. This thing is called an autoencoder. But what is an autoencoder? We're learning what an autoencoder is here. So it's true it is an autoencoder, but what is that? Well, it's this. We're going to learn with this. Dimensionality reduction is one great way to think about it. Because if you think about what's going on here, is we started out with something that was 784 dimensional, and we're mapping it down to 2 dimensionals. You can think about this step as going from 784 to 2 as kind of encoding or dimension reduction, right? This is like an encoder. This is encoding. Encode. And when you encode something that's 784 dimensions down to 2 dimensions, that is doing a dimension reduction, right? We took an object, an image that was 784 dimensions, and we're going to try to represent it as a 2-dimensional object. And then we're going to take that 2-dimensional object and we're going to decode it back to an image. Decode it. This is what people say. So the first layer you can think of as encoding down to 2, and then the second layer you can think about it as decoding. We want to take our 784 dimensional thing at one picture and write it as a 2-dimensional thing, 2 numbers, in such a way that when you decode it, the loss function, and the loss function is how far are you after you do encoding and decoding, how far are you? So you could really write the loss function you could think of as you encode x. So x is an image of size 784. You encode it down to 2, then you decode it. And then you want that to be close to the original x, right? So you take where you get to after you encode and decode, you're back to an image, and then you see how close are you to the image you started at. And you want to make that difference as small as possible. You want the process of encoding down to 2 dimensionals and then decoding to be back to x. Somehow encoding and decoding should do nothing. It should give you right back to x. So that's the idea of dimension reduction. Some of these other ones I think are not quite right. So things like logistic regression and linear regression involve a y value. There's no y values here, so that's not what we're doing. Optimizing the image, so we're optimizing the encoder and the decoder. We're optimizing the weights. So the decoder depends only on W0. The encoder depends on W0 and the decoder depends on W1. So the encoder here is just this matrix, W0, and the decoder is this matrix, W1. And we're trying to optimize those things. We're optimizing the encoder and the decoder so that when you apply it to the images x, you get back, you reconstruct the images. And we want to make this as small as possible. You want to reconstruct the images as best as you possibly can. Okay. So I'm not seeing the magic word, because we did this earlier in the course, and there was a magic word for this, where we talked about this idea. So I'll let you revote, now that we've talked about it a little bit more, and we have these nuggets of decoder and encoder, maybe we can understand it a little better. It'll remind you maybe of something we did earlier. Okay, so I'll give you one more chance to vote. And again, feel free to talk. Maybe you have an idea you can share with the people near you. Okay, so let's revote this one. Okay, there's like 10 seconds left. I think most people have answered. Okay. So here we go. I'm going to reveal the counts. This time, 5 people said PCA, or similar to PCA. Not only is it PCA or similar to PCA, it is exactly PCA. So if you do this, the mathematical optimum is, to minimize this thing, the mathematical optimum is that W0 and W1, they're matrices with 2 rows. Well, okay, or I should say W1 is 2 rows and W0 is 2 columns. But the mathematical optimum is to pick those top 2 eigenvectors and stack those 2 things on top of each other, eigenvector 1, eigenvector 2. That will be the mathematical optimum to minimize this loss function. And it's really exactly what we did before. So PCA is trying to find the directions that they maximize the spread of the things. And maximizing the spread of things is also related to maximally reconstructing the things. It turns out it's the same problem. So the optimal solution here are the eigenvectors of the original empirical covariance matrix. And when you do that, yeah, so W1 times W0, if you look at this, if you write them the other way, then this is a 2 by 784, and this is a 784 by 2. Did I get it right? Okay, well, all right, maybe it's the other order. W0, W1. W0, W1. And so this is a rank 2 matrix. This is a matrix. If you wrote it in diagonal form, it would have 2 numbers on the diagonal, and then it would have all zeros after that. So it's a 784 by 784 matrix. And if you diagonalize it, it has 2 non-zero entries because it's a rank 2 matrix, and it has all zeros. And the best optimal thing you can pick for this is to approximate the empirical covariance matrix for the data, which is also 784 by 784, by taking the top 2 eigenvectors. Those top 2 will be the top 2 eigenvalues, and the directions will be the eigenvalues. So this turns out it's a linear algebra problem as written, because everything is linear, and you just get back to the PCA solution. So what we're really doing is describing what PCA is in terms of neural networks, and in terms of this other loss function of minimizing the reconstructed error of decoding and encoding. Sorry, I should say encoding and decoding. Okay, so it's really just doing PCA in some sort of weird language. So great job to people who saw that. Let me show you what it looks like, because it's very easy to do in our code. And I'm not going to run it. I'm just going to show you guys the code because Google Colab is not letting me run the GPUs this morning, which makes it quite slow. So can I see it without, if I do this? All right. Okay, I want the preview. Okay, so, and again, you can follow along, it's in the GitHub. And it starts exactly the same way as we did before, same loading, same training test set, same plotting examples. All right, I suppose I can run it, okay. Yeah, okay, so I just won't run anything, I'll just show you in here. That way it'll be full screen, okay. So same exact code as before, same thing we did with linear regression and so on. But then I have a different thing. So I call this a linear autoencoder, which is exactly this PCA idea. And here you can see I've implemented it by just saying the layer sizes are 784 to 784. The parameters, same parameter function as before. And the linear autoencoder is exactly the code for doing a neural network. Here, I'm not doing any nonlinearities. So like if you want to apply a nonlinearity, you can uncomment that out. But really, it's all purely linear right now. And then I just get back the final thing. And I'm not doing any logits or anything like that. Really, it's just all linear with weights and biases. Okay. And so here's what it looks like: a linear autoencoder on a single example. So you start out with some image of size 784, and you get back an image of size 784. And you can also ask for the low dimensional representation. So please tell me, for some image, just apply the encoder part. So you can say, just encode the image and tell me these 2 vectors. And that will be a vector of size 2. And then you can do it on a batch. You can do it on the whole batch. And I made this loss function, which is exactly what we said before, which is the function minus the original image squared, summed over all the entries. So it's exactly doing what we did before. If you understood the code in the last 2 days, this code is almost identical. And here's the fun thing. You train it, And then you can ask it to please plot what it looks like. And here's what it looks like on initialization. Oh, this is not what this is what it looks like after training. Okay, great. So this is a two-dimensional representation, right? We have two coordinates, and I'm plotting for every single image in our MNIST data set. I'm plotting as a dot over here. And remember, it's trained only using the x values. So the program doesn't know anything about the y values. It only sees images that are 728 by 728 pixels. But just for fun, I plotted the dots with a color based on what their true value is. So this big blob of orange over here are the number 1. So for some reason, when we did this thing, we encoded all the images into their two-dimensional space. We did PCA with two components. All the ones got clustered together over here. And actually, if you look carefully, you can see other patterns. They're not super clear, but there are other patterns. So for example, over here was all the red stuff. Those are all the zeros. And the ones and the zeros are very far apart. And you might think 1 and 0 are very close together. Why are 1 and 0 very far apart? Well, if you look at them as images, a 1 and a 0 look kind of maximally different, right? A 1 is a line, and a 0 is a swirl. If it has pixels that are turned on in the middle, it's probably a 1. If it has pixels that are turned off in the middle, it's probably a 0. So you're starting to see that pattern. And you can start to see like the green things, those are like the 4s, those are like a little bit halfway between them. It's all mixed up. So what we've done is PCA with two components, two because that's the dimension of my screen, it's nice to see, on our MNIST data set. And another fun thing you can do is you can ask it to please reconstruct things. So here what I'm doing is I'm plotting reconstructions. So here is a digit on the left, that's the original thing. And then I encode it, and then I decode it, and I get a new image. And that is what the neural network is trying to do. It's trying to make this image and that image as similar as possible. And of course, you can see it's not that great. Pretty blurry blur over here, right? But some of them, it's a little bit better. Like look at that one. That's not bad. Look, the 0, it figured out, that's the 0. We went through the encoder, we got to 2 dimensions, and we went all the way back up to 784 dimensions, and we got this. And that worked pretty well. This is pretty good. And it kind of makes sense, actually, because a 0 is all the way over here on the space, right? So kind of everything over here in the two-dimensional space is a 0. And those should be reconstructed quite well. Whereas things in the middle, it's like hard. Are they going to be a 0? Are they going to be a 4? Like, they're all mixed together. It's going to be hard to tell them apart. But over here, they're clearly zeros. So we should be able to see zeros after they go through, whereas the other ones we can't see. And that's probably because one of the eigendirections is like a 0, and probably the other eigendirection is like a 1. Right? So it's some combination of zeros and ones, basically. All right. So yeah, again, here is a 4, and the 4 came back as a 0. Right? So what happened is the 4 went through the encoder. It came out as a two-dimensional point. So the 4 is somewhere here. 4 is green. So the 4 is somewhere over here, say. Right? And then we decoded it, and it looks just like a 0. It's sort of in the 0 zone. Right? So it's using the component of the eigenvector, which the eigenimage, if you want, that looks like a 0. So the 4 kind of is coming back as a 0. And fortunately for us, even though visually they look very different, the pixels are turned on in similar spots. Like this line for the 4 and this line for the 0 are kind of lining up. And so the computer is like, well, in terms of the difference between these two things, the difference squared, which is the loss function I care about, they're actually somewhat close. It's not great, but there's pixels here where there's supposed to be pixels here. There's no pixels in the middle where there's no pixels in the middle. So like it's pretty good. Like you can see why the computer thinks that this is a good solution to this. Okay. And then there's more. Like the 1 looks like that. Here is a 9. Oh, that 9 looks a little 9-y. But you can see the 1 and the 9 look pretty similar, and that's because we only have 2 eigenimages. We can do linear combinations of 2 eigenimages to get these images. Okay. So there's a 2, there's a 1, a 3. You can start to see in the 3 there's like kind of 2 blobs. So it's not doing terrible. Okay. So that is a linear autoencoder, also known as PCA. And you can see in some cases it does quite well, in some cases it does quite badly. And it is starting to reveal some cool structure about what's going on. Okay, so far we've done nothing new. This is all the things we did with PCA earlier in the course. I could say them again. So this would be a good starting point. You could do PCA first, and then try to build logistic regression or something on top of it. And it has a head start because it's separated out. So it'll be like the things over here will be 1s, the things over there will be 0s. Maybe it helps it learn, right? Or you can do other things with it. Any questions or comments before we keep moving on and getting more complicated? Okay, so far it's a repeat of everything we've done, just like when we did linear regression and logistic regression in the Colab. But now, this is the fun part, is you can take everything we've done and just apply it to the setup to make it more complicated and just do better. And so the next thing that we're going to do is we're going to do a nonlinear autoencoder. A nonlinear autoencoder. And what is a nonlinear autoencoder? It's the exact same thing, except for I make two changes. One is I can use more layers, right? So in PCA, you have two matrices. You're just looking at these 2 by 784 matrices. But we know we can add more layers. And here I've done 784, 1,000 to 1,784. And so effectively, what I've done is instead of the encoder just being one matrix that multiplies you down from size 784 to 2, now it's this 2-layer beast, right? It's a very complicated. First you go up to 1,000 dimensions, and then you go down to 2 dimensions. And the hope is that this 1,000 dimensional thing, we have 1,000 different like if statements that can sort of like learn things about the image. And the other thing I've done, and this is again the big superpower that without it nothing would change, is I've made it nonlinear. So if you look at the code, I've used this ReLU function, and I've in between layers, I first apply a linear thing, but then I do a nonlinearity. And the nonlinearity moves you out of the space of linear functions into the space of nonlinear functions, which is much, much bigger. So we're in this huge space. The possible functions we can represent are much bigger, and you get very many different answers. And here is what it looks like. So again, same exact shapes and things like that. Okay. And now I've trained it, and it took a while, but here is what it looks like. Again, the 2-dimensional space looks very different now. And you can see that it's a lot better at separating out the classes. And once again, I want to remind you, the neural network never ever saw the Y values. The neural network only ever saw the actual images, right? It doesn't know anything about the zeros or the nines. We could have had a data set where we collected and we didn't label it, right? We just like scanned a bunch of digits and didn't tell it which one's 0, which one's 9, and it would have made the same thing. But you can see it's very clearly starting to separate out the different digits. So now all the zeros are down here. Sorry, the ones are down here in orange. The zeros are up there in red. And in between you have these nice stripes, like over here, this blue stripe, those are the 6s. Is it surprising that all the 6s are near all the zeros? Well, no, because like a 0 and a 6 are very similar. How would you describe a 6 to somebody? You're like, draw a 0, then draw a little line, right? So these are things that have a big circle, and then if you go down here, you add on a little line to it, right? And then if you go a little bit more, you become a 2 in yellow. You're sort of like deleting, you leave the line part, but delete the circle part, right? And then if you go all the way over here, you become a 1. And this is only the 2-dimensional representation. You can imagine doing it in 3D, and it would be even better, right? It would be even more able to separate things out. And here are what the reconstructions look like. And you can see they're quite a lot better than the original. So here is a 5. The 5 somehow got reconstructed as a 3. Let's look on the map and see. So a 5 is this cyan tealy color, which is over here. And those are in the same region as the 3s, I guess. The 3s are the greens. So the greens and the cyans, they kind of like overlap over here. So you can see why some 5s will accidentally get reconstructed as 3s. And that's what happened. The 0 looks great. And again, zeros look great because zeros are in their own little land over here, right? In the red spot. So the zeros always look very good. This 9 and this 4, you know, it looks clearly like a 9, but in terms of pixel similarity, they're very close. And again, the 9s and the 4s should be quite close in the map. Let's see. A 4 is this green color over here, and a 9 is this pink color. And you see the green colors and the pink colors are right on top of each other in this little stripe over here. Okay. 1 looks great. This 2 is coming back as a 6. This 9 looks very good. Okay, here's a 1 where it went horribly wrong. A 1 became an 8. Where did it go? A 1. This 1 became an 8, right? And I guess it drew the stick, but it also has this stuff encoded on. And it's really hard to say what it's doing because everything is nonlinear now. So all we can say is that it went down to 2 dimensions, and when it came back, we did some crazy nonlinear function. It's not that there's like 2 components we're adding on anymore. You really can think of it as like 1,000 different if statements. And it came back as this 8. I don't know. Like, nobody knows why. Okay. The 3 looks good. Here's another 1. Oh, you can see the ghostly image of the 8, right? So this one is more like a 1, and over here, it added more of the 8 part to it. And I guess the only difference was how wide the 1 is. I don't know. So you can stare at these things and learn a lot about them. This 3 looks amazing. Okay. There's a 6, and so on. And the cool thing is, it's just a lot better. Like, I love this plot, this little map over here. If you rerun it, it's all random, of course, so you'll get a different answer. So if you rerun it, here's another alternative running of it here. So same thing, but just run a different way. So this one was, I ran it a different time, and I have another one where I ran it a different time. Here's one where it looks really good. In this one, it decided to put, next to the ones, it put the 6s. So look, it has them in a different order, right? And that's because when you're training, it's random. It's showing it different examples. The original parameters you start with are random. So it's not like PCA where you always get the same top 2 eigenvectors. When you're in nonlinear land, you're always going to get some weird stuff. In this one, the 0s and the 6s are next to each other. Oh, I guess it was the same thing before. Maybe just everything is flipped. Okay, maybe the actual order is the same. But anyway, you get some other thing, right? And you can run it and see what it does. You can do these reconstructions and things like that. And so that is a nonlinear autoencoder, and that's just one example of something you can do with neural networks. Okay, do I want to say anything else? Yeah, lots of examples. Okay. Any questions or comments about that, or different things you can do? So I'm trying to show you guys the wide world of different possible things you can do with the neural networks, and use your imagination to sort of think of how you could use this for some actual data science task. Yeah?
The PCA function that we use in scalar, is
Yeah.
that a linear?
Yes, that's linear. So if someone calls it actually PCA, that means only the linear thing. Yeah, and the big advantage of PCA is it all goes through linear algebra and like stuff that is like really well understood. Like you will never run the PCA and it'll be like, well, I gave you a bad answer. Like it'll run, you'll get the eigenvectors, and it'll work. For this stuff, it has to train the neural network. It has to do the gradient descent using the thing, and there's all sorts of things that can go wrong. Like if the step size is too big, if the parameters aren't initialized right. So it's more finicky to do, but you can get much better performance depending on the task.
I believe earlier you have shown us an example where you were using only the first 10 eigen.
Yeah.
And that translated to accurate
Right.
digits.
Yes.
But for some reason, when we are using lower or non-linear PCA,
Yeah.
with all the eigenvectors, the digits are coming up as incorrect.
Yeah. Okay. Well, I think the big difference is the dimension you are mapping down to matters a lot, and everything I've shown you today is 2-dimensional. So I've mapped down to 2 dimensions both times. I did linear with 2 dimensions, and I did nonlinear with 2 dimensions. And I was trying to show you that if you fix the number of dimensions to 2, the nonlinear is better. It's true that if you are allowed to go up to 10 dimensions, I would guess the linear with 10 dimensions is better than the nonlinear with 2 dimensions. But I would guess that the nonlinear with 10 dimensions is even better than any of those. And the reason I did only 2 dimensions is because then the map is very clear. I can show you this nice 2-dimensional map, and we can talk about where you are on the map, because the screen is 2-dimensional. Right? So if the dimension of the screen matches the dimension of the points, we can map them nicely and see. In 10 dimensions, you'll get much better performance, and these things will be like more clearly separated, and the reconstructions will be much, much better. And you should try it. So just go, go to the GitHub, download it, change 2 to 10, and then run it. It should work. You'll have to wait a while it trains. If you run the code to plot it, it'll probably explode, because it'll be like, I can't plot something 10-dimensional. But the actual reconstructions will all work.
I won't plot this, but if I use 10, the final layer of my encoding would be 10, and then again from 10 to 784. Then it'll give me accurate results even if I consider the first 10 eigenvectors.
Right, yeah, so it will definitely improve relative to the 2. I think the nonlinear one will still be even better than the linear one.
Okay.
So that's what I'm saying. Yeah, the more dimension you have, the better. And nonlinear can be more performant than linear. Those are the 2 facts. And it's not clear which effect is bigger. I guess it depends on how many dimensions you add and so on. Yeah, and in real life, like this is when people do these things, it's like a question of what dimension should be used. Because if you use a dimension that's too big, then you're sort of like not gaining the advantage of reducing the dimension at all. And if you use one that's too small, then you're losing a lot of performance. So it's like a balancing act. Yeah, you have to decide what you think is best. Yeah, great question. Anyone else? Okay, so in the same vein, so far we've done images, and I've shown you how to map images to vectors. I'm going to spend just like a little bit of time telling you how to map words to vectors. Yeah?
One quick question.
Yeah.
So aren't we augmenting the data, if you could say. I mean, we are creating new data set out of the current data set, so this can be used for the data.
Yeah, so that's true. So you could think of this as augmenting the data. And what you would do is, each image right now is 784 pixels. You could say, let's take the 784 pixels and add on 2 more to go from 784 dimensions to 786 dimensions. We would add on these 2 things. That would be augmenting it. But you could also think of, I'm going to replace my 784 dimensions by only these 2 dimensions. And that would be like an extreme dimension reduction. So, and it's up to, like, both could be useful. So you can think of this as a smart way to come up with new features to add on, or you can think of it as a way to replace all of the features. It's up to you. Yeah. Okay, so I'm going to show you kind of very briefly how you would do this kind of thing for words, not just images, right? Because images they're already a nice vector of size 784, and then we reduced it down to 2 dimensions. It's like I took a vector, and I still have a vector. I did a magic trick of making the dimension smaller. But with words, it's an extra thing, because words aren't really a vector to begin with, right? It's like the word that's not really a vector. So how do you do this with words? And the magic is that once you do this, you can do this kind of thing with words very well. And then you can start to do all sorts of crazy things. So I want to show you one really cool application, which I'm sure you've seen on the internet now, which is doing image generation. And so this is, you type in on the computer, a corgi playing a flame-throwing trumpet, and then the computer does some magic and it outputs a picture like this. Like it understands what you said in the words, and it produces the image. And actually, this is just what we just did in MNIST, but on steroids in some huge way. And what it's doing is it takes the text you wrote, it has an encoder that encodes the text to some low-dimensional space. More than 2 dimensions. I think they use 300 dimensions. But it takes the text, it turns that into a vector, and then on the other side, they have a thing, an image encoder. They take images, and they turn those into vectors. So they take the text, they turn it into a vector. They take the image, they turn it into a vector. And then they have some magic in between that is going from hidden dimensional vectors of words to hidden dimensional vectors of images. And it takes, it matches these 2 up. That's really the magic they did. So they had a big data set of labeled images, and they used that data set to match these 2 things together in a way that can generate. So when you say, please generate an image of a corgi playing a flame-throwing trumpet, it maps it into the vector space of text. Then it takes that and uses their system to create a vector in image space, and then they run the decoder to make the image. So really what they're doing is a very fancy version of the extremely simple thing I showed you over here, which is like if someone was like, please generate an image of the number 2, what I would do is I would take 2's, map down into this yellow space, and then I would sample along somewhere in the 2 space of yellow things, and then I would come back with a decoded image, and I'd be like, here's the 2 you wanted, right? They're doing a very fancy version of that, where it's still the same main idea of encoding as vectors, both text and images. And by doing that, you can connect them up in this latent space. You can do all sorts of magic tricks. So I want to show you just like the very basics of this text encoding idea. And I'm not going to show you the fancy one they used. If you guys want, you can vote for that and see some of that next week. I'm going to show you a very simple version called word2vec. Let me find word2vec. Should be one of these. Yeah, here it is. Word2vec. Okay, so this is a website called the Illustrated Word2vec. And Word2vec, I believe it was from like 2013 or something. Word2vec. Does it have the year? Well, okay. It's something, so it's like a precursor to all these things, but still relatively recent. And the very famous example in Word2vec, we're embedding the words king, man, and woman into vectors. Here they're represented as vectors of size 4. And the point is that men and women, because they perform similar functions in speech, like any sentence where you say, the man did blank, you could also say the woman did blank. Like man and woman are sort of related in terms of their meaning in words. Because these are related, they should have similar vectors, and they do. And because they have similar vectors, you can do all sorts of cool things. The really classical example, I'll start with this classical example, is that you can tell it, so here are the actual vectors. In this word2vec thing, there are actually 300 dimensional vectors. And you can see the man and the woman vectors are very similar. Like they have the similar values in all of the 300 dimensions. And there's the word king here, and the cool thing is you can really do this is actual code that ran, and you can say, please find the most similar word, right? Most similar means in the vector space. So of the vectors in that hidden dimensional vector space, just like this image that we had over here, right? In that space, please find the vector that is most similar to king and woman and furthest away from man. So you take like king plus woman minus man in some sense, and you say, what is the vector that is most similar to that? And it finds the highest answer with an 85% similarity is the word queen. So somehow it figured out that if you make a king, you take the idea of a king and you subtract the idea of man, and then you like add on the word woman, that gives you the word queen. So it's kind of like understanding what these were. Okay, and here are some other words that are close. So this is kind of this king minus man plus woman is approximately queen in some sense. Yeah.
So let's say the embedding that we have for individual words.
Yeah.
Basically, we're trying to find the equilibrium distance, or is it like the k nearest neighbor?
Yeah. So I'll tell you exactly, or very roughly, how they find the vectors. Right now, so far, I'm telling you what the vectors do. Right. So it's true. I haven't told you how they're trained yet. On MNIST, it was this reconstruction idea, right? You go to the vector space and then you come back and reconstruct. And it's going to be a very kind of similar idea, is that we're going to try to reconstruct sentences in some sense. So we're going to look for sentences that have the word man in them, and we're going to say we're going to replace man with a vector in a way that anything that is close to that vector should fit in the sentence. And that's why man and woman will be similar vectors, because they both fit into similar sentences. You'll see that in a minute, but that's like the extremely high level idea. Yeah. I'm not sure if I answered your question.
Yeah.
Okay. Okay, so that's what we're doing. This is a really nice tutorial, so you can go through and read the whole thing. It starts out by telling you what vectors are, and it's like you can think of things as vectors. We know that idea, so let's go into the nitty-gritty of how we actually do it. And in this original thing, so there's two papers that came out at a similar time. One is called Glove, and one is called word2vec. And they're both the same kind of idea. And the way they create these embeddings, so I've shown you what the embeddings do, but let me show you how they are made. And the way they are made is they look at filling in blanks. Okay? So they take fractions of sentences and they say what word would fit into the next slot. And the example they give on this website is thou shalt blank. So thou shalt, input 1, input 2, blank. And the answer is not. And the reason it's not is because there are many sentences where thou shalt not starts the sentence. And one example they gave is a lot of these things were trained with Wikipedia as the input text. And in Wikipedia, there is somewhere where it says, thou shalt not something a robot. Where did it go? It's from The Matrix. I had to include it because I like The Matrix. Okay, I can't find it. It's gone. Oh, here it is, yeah. Thou shalt not make a machine in the likeness of a human, right? So there's a lot of sentences on Wikipedia that start with thou shalt not. So in our data set, we have thou shalt not, and so not will be the right thing to do it. So how are we going to encode this? Well, we make a data set by looking at sliding windows. So we take all of the sentences in our data set, say Wikipedia, and we make a data set that has 2 inputs and 1 output. For the 2 inputs are the first 2 words, and the output is the next word. So thou shalt not gets added to our data set. Thou shalt not. And you can do this for, slide it over it, shalt not make, and so on and so on. And you get this huge data set of inputs and outputs. And then what people do is they train the vector embeddings to kind of match the inputs and the outputs. Okay, so, and you can do this both ways. So you can have the input and output go after too. So by a blank bus in, you could put by a bus in as 4 inputs, and then red is the middle word, is the output. So this sort of, how you set it up, you can make the order work however you want. Okay, someone got hit by a red bus, okay, making a machine, and so on. So these are the input words and the target words, and you make this big data set. And then what you do is if you treat it just as pairs, what you do is you set up a vector embedding, so you search for all the possible matrices, all the possible vector embeddings. What do I say when I say you search for it? I mean you do gradient descent. And the loss function you have is the embedding for the input word and the target word, are those close together? And if the embeddings are close together, then you get a good score. And if the embeddings are far apart, then you get a bad score. And then we just iterate that over and again. Right? This is the beautiful thing about these neural network methods. As long as you can say what is good and bad in your loss function, you can, in principle, try to find a good solution through gradient descent. So they do that, and they start creating. So we're essentially predicting the next word as our task. If you have a good prediction, then you get a good score through the embeddings. And by doing this, you get good embeddings. And the reason that man and woman have similar vectors is because the pairs, man and woman, will appear in similar contexts. Like any sentence that has something, something man, the same sentence could have something, something woman, and that would also appear somewhere in the data set. And therefore, when you look for solutions, you tend to find a solution where the two vectors for man and woman end up being kind of similar. And that's why you can do all the math of things like that. And there are a lot of actual like little details that you can look at. So one thing, I think they had a nice thing, which is the context window. Yeah, okay. So the things are called context. And I think they had a nice little discussion at one point here. Yeah, okay. So different tasks are served by different window sizes. So depending on how you choose the size of the window, you will get different vector embeddings. And one thing they say is if you choose a smaller window size, like 2 to 15, you get embeddings where high similarity means the words are interchangeable. So that's what I was talking about with man and woman, right? So any sentence where man appears, women could equally appear equally well, and that's why the man and the woman vector will be sort of similar. But if you use large window sizes, like 15 to 50 words, then you get relatedness. So it'll tell you these two words are related to each other because they appear in similar contexts. And because the context window is larger, then you can kind of like have a more abstract. You have more room to like add in words that kind of like explain the relationship, right? So maybe the word octopus and the word 8 have similar vectors because any long window where the word octopus appears maybe has an 8 talking about its tentacles somewhere, even though octopus and 8 aren't really interchangeable words. If you have a long enough window, they'll appear together similarly enough. So this is one way to do it. There's also some stuff you can do with negative samples. So to kind of increase your data set size, you can say, well, these words never appear together. So please make sure these vectors are far apart. And that's another thing you can do. So that's at a very, very like broad level. That's how these vector embeddings work for words. And once you have vector embeddings for words and vector embeddings for images, you can do all sorts of crazy cool magic stuff. And this is also like the basis for how ChatGPT works. So this plus 10 years of research is how we got ChatGPT. Any questions or comments about that? Okay, so the next thing I want to do is, like I said, we're going to vote on fun topics. What are we going to do next week? Because I'm sort of like, we're done all the stuff that I really said we should really do in this course. And so everything else that we're going to do next week in the last 2 classes can be whatever you guys sort of want. And here are some options. 2 of the options are things that we talked about already. So more machine learning image stuff, so like convolutional neural networks, like doing even better on the MNIST data set, things like that. More machine learning natural language stuff, so we could go harder on this natural language stuff. I'll give you a quick preview of what we would do if we did that. There is a really nice tutorial online that I really like. Let's see if I can find it. Here it is. So it's by this guy, Andrej Karpathy, who used to be the head of AI at Tesla, and he made a really nice thing online called Make More. And Make More inputs a data set, and then it generates more things that look like it. And the data set that he did is children's names. So the data set is Emma, Olivia, Ava, and so on. And at the end of the document, it trains a neural network that does vector embeddings, not on words, but on letters. So it vector embeds the letters A, B, C, D, E, F, G, and then it uses the vector embeddings to try to like generate the next letter in the thing. And the really cool thing is there's a really nice spelled out tutorial, so you can watch it and know all the details. Like it really goes from start to finish, and I'll explain a little bit of it in class. But the cool thing is you get this kind of picture. So here's the neural network like training, right, and the loss function going down, and you get this kind of vector embedding. If you do it in 2 dimensions, you get a vector embedding like this. So he's embedded all of the letters of the English language into a 2-dimensional space, and then use that to do things. And you can see all the vowels. Like the model doesn't know what a vowel is, right? It just knows letters. But it found the vector embeddings for all the vowels, A, E, I, O, U, Y, are all in the middle. And then these ones are all one kind of sound, S, T, Z, M. And those are some other ones, C, P, K, D, very different Here's another character. Dot is a special character. That's on its own over here, right? Dot is on its own. So it's sort of like discovering things about language on its own. And the fun thing, the really fun thing, is at the end of the document, we generate some baby names by just running this and say, please predict the next letter. So this is like baby ChatGPT, right? So ChatGPT normally generates like word by word, or token by token, which is essentially a word. This generates letter by letter, and you get these like hilarious names. Like you're gonna go home and name your kid Kim Lithy or Carla. Oh, that's actually a word. Sometimes it's like way off, you know. Haas. I'm pretty sure that's a type of avocado. But so that's a fun one we could do if you wanted to learn more about natural language stuff. Okay, what were the other two options? The other two options I have on here are tree-based methods and boosting algorithms, which I know some people did on Project 1. And let me show you a very quick preview of what that looks like. Is this right? Yeah, okay. So what this does is it generates classifiers that instead of being things like linear combinations and involving like neurons, you can think of them as being made of decision trees. So, for example, if you wanted to classify an animal, what animal is this? Instead of doing like linear combinations of features of the animals, you would ask questions about things. You'd say like, how big is the animal? Does it have 2 legs? Yes or no, and so on. Right? You have this like question tree, and this question tree divides the space of possibilities into these regions that look like this. So here's some data set. We got red, yellow, purple, and teal, and here are some trees that you could get. And you see the trees kind of like divide things by asking questions. A question is a yes or a no in one of the dimensions. And that makes a division that is a straight axis-aligned line. So here's the first question. Are you above this line or below this line? Second question. If you answered yes to this question, you're below it. Are you to the left or to the right? If you answered yes to that question, are you above it or below? So you end up with classifiers that look like this. And these are called tree classifiers. And the cool thing is there is a way, the tree classifiers on their own are not that great. They're kind of like meh. But there's a cool way you can combine many tree classifiers, each of which are kind of bad, into one superpowered tree. And that's called a random forest. You have many trees, you can get a forest. And you can get quite a good performance with these classifiers. Okay, so there's one tree, like I said, these pictures, and you can combine them to get an ensemble of trees. And there's bagging and boosting, which are ensembles of these trees. And that's quite a popular algorithm. So in some situations, these are the best algorithms you can get. So here is the final thing you get. Each individual tree is always axis aligned. But the final tree, the final forest you get by combining many, many trees can have very complicated boundaries by combining different trees. And you can see it does quite well on this particular data set. It does a really good job of separating them out. So that's, if you want to learn about that, so the famous package XGBoost is doing boosting of trees. And trees didn't make it into the name, even though that's really what it is. Okay, so that's one possibility. And then the very last possibility is something called support vector machines. And support vector machines have a similar idea of trying to make a classifier by using hyperplanes. So if you want to classify these red points from these yellow points, as a human, you would just like draw a line in between them. You say if you're above the line, it's red. If you're below the line, it's yellow. And that's what a support vector machine does. It finds a hyperplane. So in 2 dimensions, it's a hyperplane. In 2 dimensions, it's just a regular line, but in higher dimensions, it's a hyperplane that separate the data. And the problem, the mathematical problem, is that there are many hyperplanes that do this. There's more than one answer. But support vector machines find the best possible answer in some sense. So there's some kind of like best possible line to go through here. And support vector machines tell you which one is the best possible line in a nice mathematical way. And then once you've done this, and you've done a good job with this, there's a really cool trick called the kernel trick, which I think we very briefly talked about later on, which lets you do it for nonlinear points. Oh, by the way, the reason they're called support vector machines is these vectors that are on the boundary, these 2 red dots and this yellow dot, they're called the support vectors. And you can think of them, they hold the whole hyperplane in place. If those points were to move, then the whole hyperplane would move. Whereas if you move some point down here, it doesn't change the classifier. But so the cool thing to me, all the stuff about support vector machines is kind of like ho-hum, whatever, until you get to the kernel part where it makes it nonlinear, and then it just goes like completely nuts and becomes quite exciting. So here's one, right? You have red and yellow points. And you're like, well, there is no line that separates the red and the yellow points. But there is this trick to take a hyperplane in a different space and use a kernel function instead of a inner product. And if you do that, you essentially map to this space. And now there is a plane that goes through. So you make a plane that like slices it just down the middle, and everything above it will be yellow, everything below it will be red. And so you end up with a very nice classifier. So this is the kernel trick, which is a great trick to know. And you end up with classifiers like this. So the hyperplane, not in ordinary space, but in the magical high dimensional space, can make circles and things, and you can classify things like that. So that's one option. Okay. Great. Okay. And there's all sorts of ways to do it. So these were really popular before neural networks. This was the hottest thing before neural networks took over. It's still useful for some things. Okay. I think I've explained all the different options on the menu for next week. Have I? Oh yeah, another option is we can have some in-class time to talk about the final projects. And you should feel free to vote for as many of these as you think are interesting, and we'll do the ones that have the most votes. So you can vote for more than one. You can approve of however many you want. Any questions or comments about any of these things? Okay, should I wait longer? Should I just do it? We have 12 votes. 1, 2, 4, 8. I think there's 13 people in the room. Okay, great. All right, everybody voted. So let's see. What are we going to do next week? Next week we will blank. Okay. Review responses. Okay. Natural language stuff. Great. So I will give you guys the link for this video, and we'll do that. And we'll do some boosting. And then if we have time, we'll do, actually this one would be a good one. We'll definitely do that. And if we have time, I'll also do convolutional networks. So we'll do the top 4 there. I guess support vector machines. And yeah, GLMs, I didn't mention GLMs, probably why they didn't get a good vote. But okay, you guys have had enough of the regression-y type stuff. So great, so we'll do those. I'll send the link out, the links for this stuff. So if you're into this stuff, there's these really, really good tutorials online. They're quite long. They're like 2 hours long, but it's like so good. It's like crack. Like you just like watch it. It's like you understand everything. There's nothing I've seen that has like that density of learning on the internet. So I'll send those around. They're really good. Okay, see you guys next week. And don't forget to finish your project and vote on final project topics.